Hello everyone. Welcome to the 2020 Minnesota Youth Institute Immersion activity. Of course, we would love to meet you in person here on the St. Paul campus at the University of Minnesota, but because of the global pandemic, we are unable to do so, but looking forward to interacting with you with this virtual event. My name is Jake Youngers, and I'm an assistant professor in the Department of Agronomy and Plant Genetics here at the University of Minnesota. I teach classes and do research on topics related to sustainable agriculture. Although I don't have a background in farming, I did not grow up in an agricultural community, I was always passionate about the environment and nature. That passion led me to pursue degrees in conservation biology. Those degrees set me down a career path to try to solve environmental problems through agriculture. So let's review some of the environmental issues that are related to annual row cropping. Annual row crops, which have really shallow root systems, so that they can put a bunch of their energy into big seeds and lots of seeds. These annual row crops with shallow root systems only live for about 4 to 5 months out of the year. The remaining time, that land is left fallow, and that means the soil is exposed to wind and water and can be washed away, swept away, which is what we call erosion. Perennial crops can reduce soil erosion because they have deep, dense roots and the perennial plants stay alive all year round. Even in the winter months, perennial crops provide cover so that the soil cannot be blown away or washed away as easily. The deep, dense roots also help build organic matter in that soil, which could make the farm field more profitable for farmers. In the video you watched before this, about why our agricultural system is broken, you learned that most of our crops are annuals. We don't have any perennial grain crops until now. But why is that? So why are all of our crops annuals? Well, because an annual plant only has one shot to reproduce, 1 year to produce seeds, it almost always produces either really big seeds that are really sure to survive, or they produce lots and lots of really small seeds. On the other hand, perennial crop has the luxury of waiting for a good year to produce seeds. Think about an oak tree. Some years there's lots of acorns falling from an oak tree, and other years there's not. So a perennial crop can wait for the conditions to be right to produce those seeds, to ensure that those seeds actually turn into young plants. So if you're thinking about crops, we don't want crops to just wait for a good year to produce seeds. We need crops to produce seeds every year. And we need crops to produce big seeds, or lots of them, so that we can get the most food from an acre of land. So that's the inherent challenge, is finding a perennial plant that can produce lots of seeds, or big seeds, year in and year out consistently, so that farmers can rely on getting a profitable yield from that crop. Here at the University of Minnesota, we're developing the world's first perennial grain crop. We're taking an old forage grass called intermediate wheatgrass and breeding it so that it has larger seeds and more seeds, so that farmers can use those and sell them profitably for grain. We're sitting here in a field of new and improved lines of intermediate wheatgrass. The grain that's harvested from these new lines is called Kernza. And Kernza is the world's first perennial grain crop that has nutritional benefits for humans, provides ecosystem services, and new economic opportunities for farmers. So here's an intermediate wheatgrass plant. This is one plant. You can see it has lots of stems and lots of seed heads coming off of those stems. The plant itself stands about 3.5 feet tall, but it has roots that go down at least 3.5 feet. Here's a picture of a Kernza plant that was taken by Jim Richardson from National Geographic. This plant was grown at the Land Institute, a partnering nonprofit organization in Salina, Kansas, that has been working with us to develop Kernza. The gentleman here is holding a plant that was grown in a specialized chamber so that we could see the roots after it grows. The big question is, how deep do the roots really get in soils in Minnesota and in soils in different types of growing regions across the United States? That's what we've set out to determine with this project. So how deep can Kernza roots actually get? Some people have measured Kernza roots as deep as 9 feet below the soil surface. Here in St. Paul, Minnesota, we easily see roots getting down to 3 feet deep and sometimes deeper. We're also interested to know how much roots are at various sections of the soil profile. So, are there more roots in the shallow part of the soil, or do we see more roots in the deeper parts of the soil? That's what we're trying to figure out here in this study by taking photographs of roots at various depths. To study Kernza roots, we use a specialized camera called a mini rhizotron. The mini rhizotron is a camera that's about 8 inches long, and it fits into a clear tube that's buried right next to a Kernza plant. This clear tube is about 3 feet long and sits right next to the roots of the plant. The camera is inserted into the clear tube, and then it stops and rotates to take a picture that's 360 degrees in circle so they can capture all of the roots growing right around the tube. The camera is then inserted further into the tube to continue collecting images at deeper depths, all the way down to the 3-foot depth. Here's a raw image collected by the rhizotron camera. You can see the roots growing up alongside the clear tube. Next, the research team traces the roots using a specialized software program. By tracing the roots with this software program, we can measure the length of each root. After the length is measured, we make adjustments to the trace to account for the diameter of the roots. And that's really important because roots with a larger diameter, or coarse roots, decompose slower than fine roots. And we want to know how long these roots actually stay in the ground, how fast they die, and how fast they grow. So we also need to measure the fine roots and measure the diameter of those as well. We take photos of roots at least once a month, and then we trace those roots and compare the images from 1 month to the next. Here we can see a comparison of the exact same plant and the same depth from images in May and August. And we can see that some roots died over that period of time and some roots grew. We've also learned that about 50% of all of the biomass, all of the weight of a root, is carbon. And that was carbon that was pulled from the atmosphere during photosynthesis and moved down to the roots. And that carbon that's in the roots now might someday turn into organic matter and eventually soil carbon, where it can be stored for decades or maybe even centuries. This activity helps solve climate change by pulling carbon that was once in CO2 out of the atmosphere to reduce global warming. So let's recap. Today we learned that most of our crops are annuals, and that annual crops don't produce a lot of root biomass, so that they can produce lots of seeds and large seeds for high grain yields. However, this presents some environmental challenges like soil erosion and greenhouse gas emissions. Here at the University of Minnesota, we're developing the world's first perennial grain crop called Kernza. This crop produces deep, dense root systems that provide environmental benefits while also producing nutritious, high-yielding grain. We looked at one way that researchers can measure and monitor root growth at various depths and throughout the growing season. And this information is really important for helping us quantify the environmental benefits of this new perennial grain crop.